Again, I just want to thank everyone for joining us today on our webinar Wednesday. The topic for today is, when do I need to run a nonlinear study, a look into when a linear static is not enough. So really what the goal is for today is to see what the differences are between a linear static study and when you may need to get into a nonlinear study. Again, my name is Silvio Perez. I'm the Simulation Product Manager for Hawkridge Systems. I've been at Hawkridge here for a few years now, and I'm primarily focused on simulation. So I do a lot of simulation classes, and this is a topic that comes up a lot in my intro class as far as when do I know that a linear static is enough and when should I be considering a nonlinear study. All right, so the topics for today are going to go over a few things, a few of these things here. The first thing is to always talk about what the assumptions are. And it's always a good point to start at a linear static study. So we're going to be talking about what assumptions are in a linear static study, what classifies as a nonlinear problem, and then we're going to go into some of the capabilities of what a nonlinear study can do in SOLIDWORKS simulation, and then interpret those results as far as what we look at in a linear study, and then what we can look at in a nonlinear study as far as results. And then we're going to take a look at, or not really look into the interface, but kind of talk about another way of doing a nonlinear study for a more advanced linear study with SIMULIA Abaqus. All right, so in terms of linear versus nonlinear, hopefully you guys are kind of familiar with the simulation products. And that being said, I do want to throw up a couple other polls here to see, so I can get an idea as far as what you guys are utilizing. So for one thing, I want to know what your primary stress analysis tool is. So what you should be looking at now, or what you should be seeing, is another poll. And I want to know, do you even do stress analysis? Are you just kind of reviewing this webinar to see, what we offer? Or are you using SOLIDWORKS, or are you using any other advanced level stress tool? So I just want to get a gauge as far as what you're actually using. So looks like for the majority, it makes sense, are utilizing SOLIDWORKS. A few of you are not using a stress tool, and some of you are actually using Abaqus, which is great. It's something that we offer as well. So that being said, and this is now a little bit more directed towards the users who are using SOLIDWORKS simulation, I want to know are you using specifically SOLIDWORKS Simulation Premium to run any nonlinear analysis? So simple yes, no question. I just want to know kind of where you're at in terms of the package that you have, whether you have Simulation Premium or Simulation Standard. So, okay. Giving it a little bit of time here to have people to vote, allow people to vote here. And okay, so great. It looks like the majority of the audience are not using SOLIDWORKS Simulation Premium for their nonlinear analysis. So, but some are. So this is a great opportunity here to kind of see where we can take this to the next level. So where I like to start off with that is, again, talking about the simulation packages that we offer. So in a linear static study, there's a couple ways that you can get that. One is if you have SOLIDWORKS Premium, which is the highest level CAD package, you can get your linear static study on parts and assemblies. If you're moving towards the actual simulation packages that you can tie into any level CAD package, you can then get a simulation standard seat, which also gives you linear static assemblies plus additional other tools like fatigue analysis, being able to see what your cycle life is based on the loading that you produce from your linear static study. Right? But when we graduate, or once we kind of decide that we do need to take or utilize a nonlinear solver within simulation, we need to graduate to a SOLIDWORKS Simulation Premium. And that's the package that allows us to do this nonlinear type of problem, in addition to some other advanced problems like a dynamic problem. But in terms of packages, if you need a nonlinear or if you have a nonlinear problem and you want to use SOLIDWORKS simulation, you have to graduate to Simulation Premium, which again gives you everything that you see on your screen here. Right. So that being said, what classifies, or what do we take a look at when we're trying to do a linear static study inside SOLIDWORKS simulation? What are the assumptions that we need to be aware of before we run an analysis? The first one, it's a very important one, is that we can only account for linear elastic material models. So on the right hand side there, what you're looking at is a stress strain curve, of course, and what you're looking at is, the linear range here. And then we can see that we have the yield strength and the plastic range that a material may encounter. When a linear static study, it assumes that the behavior is always going to, the material is always going to behave linear elastically. So as we're deforming the part or the assembly, the more strain we have, the more stress we have, and SOLIDWORKS simulation for linear static is only really good for the linear portion before it hits the yield strength, right? So that being said, it can only account for small deformations. So that's another assumption that we make, is that no permanent deformation. If you remove the load, the model goes back to its original shape. Now, if we wanted to get it beyond yield, or if we wanted to load it and it was going to go into the plastic range, then that's when we would need a nonlinear problem or a nonlinear study. The other assumptions that we have as well is that the response is proportional to the applied load. So for instance, if I were to apply a load and I get some deformation, if I were to double the load, I double the deformation. So that behavior of force and displacement, it behaves linearly, right? So anything aside from that also is classified as a nonlinear type of behavior. And then in the discussion of loads, the loads are also applied slowly and gradually. So what that means is that we don't have any control in terms of when that load or how fast that load is being applied to your part or your assembly. Right? So it's really important to be aware of the assumptions of a linear static, because it explains how far you can take it within the realms of these assumptions. Right? So in order to understand this a little bit better, I'm going to go into the interface here, SOLIDWORKS Simulation 2017, which is the latest version that we have here. And I'm going to turn on simulation. And what we're going to run an analysis on is kind of the behavior on a simple pen cap, right? I don't want to distract the concept of the webinar with a very complex model, but this little simple part here is a great example to explain the difference between linear and nonlinear. So as far as setup, just so you guys are aware, you see that I isolated the pen cap, and what I want is to restrain the pen cap or the clip to the cap with the simple fixture and apply a load in the opposite Z direction there. So what I ended up doing here is, again, I applied a material, and again, if you're new to simulation, we can utilize the material database from SOLIDWORKS CAD, but you notice that for a linear static study, the material model type that we have available is only a linear elastic, right? So again, what it's assuming is that the properties that it's going to take into, it's only going to be recognizing the elastic modulus here, right? So we don't have any definition within a linear static as far as what's going to happen post yield. So that's one key thing to note about a linear static. So I applied the material. Again, I applied a fixture here, a fixed geometry, very simple, and I applied a load on the upward direction, right? And the results that we get are, of course, displacement is the main unknown for a linear static, and then we get stress, right? And you see in a linear static study, you see we kind of superimpose the results with the actual original shape of the model, and you see that there is some displacement there. Note that the deformation scale is at 1, so you see that it's deforming a lot. And you see that on the right hand side in the legend that the stress results exceeded the yield. So that's already kind of a red flag in terms of the stresses that we see here. It's already a red flag as far as, is this the right analysis type to run this type of problem? So not only is it exceeding the yield point, but it's outputting a really, really high stress, right? So In this case, if I were to look at this, if I were to run this problem and I see that there's a pretty large stress here, we can't really take into account and say that that max stress that it's outputting here is the true stress that the model is going to see, right? Essentially, we've exceeded, the assumptions that we make for a linear static study here, as far as small deformation, only living within that linear range, we've exceeded that within this linear static study here, right? So that's one thing where, as far as asking the question, when is it enough? When is a linear static is enough? Well, in this case, we can't really take into account these high stresses because it's exceeded yield and it's violating the assumptions that we take from a linear static study. All right, so that's one of the main things to look out for when you're running this study type. All right, so that being said, when we go into a nonlinear problem, how does that differ? All right, so the first thing that we need to ask is, well, what classifies as a nonlinear problem? And the first one, again, we start off with the material. Well, that's when we want to account for, just inherently nonlinear materials, like plastics, rubbers, or maybe we want to know specifically what's going to happen post-yield. And again, or maybe we want to deal with, again, hyperelastic materials, which is what we can do in a nonlinear, like, again, rubbers and really nonlinear type of materials. So that's one category that already differs from a linear static. The second category is geometric nonlinear, which means that it can account for large deformations. So that rule that we had for linear static is now lifted with a nonlinear. So we can deform a shape of a part or an assembly a little bit more, with the nonlinear, right? So we get a more realistic true behavior of the model. And then the last category deals with contact, when the size of the contact region changes during the analysis. And that's really what you're seeing here with the top clip. You see that we can't really do that type of analysis with the linear static because the contacts are changing as the part is moving. So if you have any type of analysis where that's happening, you automatically have to default to a nonlinear problem, right? And then the other categories, again, if you already are, based on the load that you're applying, you can already make the assumption that it's going to have a large deformation. Again, nonlinear problem. And then, of course, if your materials are inherently nonlinear, or you're interested in seeing what the stresses are post-yield, then you have to run a nonlinear problem. Right? So those are the main differences there, and that's really what I want you guys to get out of this webinar in terms of when is linear not enough and when we should take it to a nonlinear. As far as some of the capabilities with the nonlinear problem, or a nonlinear study within SOLIDWORKS Simulation Premium. So what you're looking at on the left-hand side is that same database, and you see that within that database, when you have a nonlinear problem, you see that there are a few materials here that have an SS next to them, and what that stands for is a stress-strain curve. So SOLIDWORKS Simulation has all this data embedded within the software that, in this case, the alloy steel has an associated stress-strain curve, right? And that's what I've identified here. And you also see that I have more material model types. Aside from linear static, aside from a linear material, you can define this plasticity von Mises, which defines a stress-strain curve. Or again, if you're dealing with rubbers and hyperelastic materials, we have a hyperelastic material model. And when you review the stress-strain curve, again, I didn't input that manually. That's embedded within the software. You see how the stresses are going to change, due to that. Essentially what you're looking at is the plastic range of your stress-strain curve. And you definitely have the option to define your own material. Therefore, you define your own stress-strain curve if you have something a little bit more custom that the original database may not have. The second category, or the second capability that we have in nonlinear, is a time-based loading. So in linear static, we assume that the loads are being applied slowly and gradually. When nonlinear, we have control of when that load is being applied as a function of time. So if we wanted to do, a kind of a high, quick load applied to the model, or if we want to vary the load as time, as the model deforms through time, we can control that. And the last thing, very similarly, is we can now control the fixtures in a time-based manner as well. So essentially what I can do with that is what you're looking at here on the right-hand side is I can say for this specific reference geometry, this fixture essentially, I want it to move from 0 to some time, and then I want to turn it off, so I want to ignore that fixture and then maybe keep it off or turn it back on, so you have full control as far as when your fixtures are being applied and when they're going to account in the actual analysis. So now what I want to show you within the interface is that nonlinear type of problem. So when I go into my completed set here in the nonlinear, you see that all I did was just copy it. The restraints are the same, the loads are the same, but there are a few key differences within this nonlinear problem. Right? So the first thing is when we look into the material, just like what I showed you in the slide earlier, we have that stress strain curve associated to that material. You see that my material model type is set to plasticity von Mises. And right now, create stress strain curve is grayed out because we can't customize any of the default materials. But if I go into tables and curves and go into stress strain curve, you see that there is that curve defined for that material. All right, so we're now defining what's going to happen post yield. And then when I run the analysis with the same load, we get the same displacement. But when we go to stress, you see that my max stress now is really close to the yield strength of the material defined. So already we're seeing a difference in terms of the overall results. We're getting a more realistic, or a more accurate, I should say, result with the nonlinear because we're now accounting for those assumptions that we couldn't do in a linear static. A large deformation, being able to see what happens post yield. So now my results are more accurate relative or compared to that linear static study. Right? You see that the max stress is closer to that yield point there. So one rule of thumb that I offer people sometimes is if I go back into that linear static study, I mentioned that this was set to 1 scale, and it's kind of a rule of thumb. You really have to look into the situation of your study, but you see that the deformation scale is at 1. If you can visually or physically see a change in displacement from the original model to the deformed shape, that may be an indication that it's not a good fit for linear static study, right? Because again, we're assuming that linear static accounts for small deformations. So if we were to run the analysis and we did have a small deformation and we set it to 1 scale, we shouldn't really be able to see the physical change from the original model to the deformed shape. So already that was kind of a red flag for me, and a good indication that's probably a better fit within a nonlinear material or a nonlinear analysis. Okay, so that kind of explains the first category, which is implementing that nonlinear material. The second category was pretty much what I had here, just to kind of show you, was time-based loading, right? So being able to control the load as a function of time. So if I go into this repeated loading category or study, again, exact same material, or excuse me, exact same setup, but what I have defined here when I go into the definition of the force, I'm no longer applying a constant force along the split face. I still define the same value as far as the load, but now that load is varying with time. So this is what we get in addition in nonlinear analysis. So when I edit that curve, you see that my left column here is the time domain, and my right-hand column is the multiplier. So what that means is that at 0 seconds, it's going to see a load of 0 times whatever value I put in for that direction. At 0.2 seconds, it's going to see a load of 1 times this value here. So you see, essentially what we ended up getting was that load is going to behave in this manner, in this on and off type of behavior. All right, so we can get more complex loading conditions within this technique that is available within a nonlinear problem. All right, so when I do that, when I accept that and run the analysis, we get the traditional displacement, stress, strain. But now, take a look at this little note here. We're seeing the max results at 1 second. So essentially at the end of the study run. When I animate this here, what you're going to take a look at is now the analysis, well, for one thing, it's deforming in this type of on-off type of behavior. And you're seeing that it's loading in all these plot steps and showing you, how it's deforming as a function of time. So what that also means is that right now, again, I'm looking at the stress results at 1 second. What if I wanted to know the stress results at half a second? So if I edit the definition of that stress plot, we now have this plot step here, and if I go to 0.5, it's going to load in that plot step here, and when I hit OK, you see that my max stress changes at that time, right? So not only are we seeing the stresses as a function, or not only are we seeing the stresses, but we're able to see the stresses as they develop as a function of time, right? So we have full control of how we can apply that load. We can make it faster. We can apply it at just an instant of time and then see what happens. But you see that we have that control in terms of lifting that rule that we had initially in linear static. We can now control it with the time domain. All right. So those are the things that we can do in a nonlinear problem. The last one here was as far as what classifies as a nonlinear problem was the context, right? So as far as we saw the nonlinear as far as being accounting for large deformations, we saw how we can incorporate the materials, but now this contact here, pretty much being able to see this type of scenario, well, it's a very simple setup, and what I have here is, now the entire full-blown model in the sense of I want to know, what the stresses are when I snap that cap into the pen. All right, so what I ended up doing was adding a prescribed displacement on this face saying I wanted to travel the distance of whatever this initial gap is. Right, and when I ran the analysis, I get something like this, where I can animate this and see as it's going into the pen, and right now the pen is there as far as the actual shaft, but you see the stresses that are developing as it's going into the pen itself. Right? I can view the displacements as well, so all those results that you're familiar with linear static, we still get them, but now we can view them as a function of time. Right? And we can see, the neat thing about this that we can do is that we can see what the reaction force is, as far as how much force is required to actually snap that cap into that pen. So I can go into the result folder here and say, give me the resultant force. I can, select this face here as far as my fixture. Let me change my units here. And then if I graph this, essentially what this is showing me is that it kind of required, almost like 3 pounds in this case, based on the material that I defined, as far as the peak load. Right, so you see we can get pretty in-depth results in terms of running this nonlinear problem and seeing what the reaction force is needed to snap that pen or that cap into the pen there. Right, so those are some of the basic, the more common functionalities of what we can do in a nonlinear problem. Again, the last thing that I wanted to show you is in a similar note as far as that loading conditions, as far as a time-based loading, which is the time-based fixture, that having that on and off. I have another example for you here to illustrate that a little bit better. So the example that I have is a model of a side panel of a drone. And the side panel is getting clipped into 2 posts. So I don't have the image of the drone here, but essentially it's a side panel. And I want to know what the stresses are as this is getting clipped in and out of that post. Right? So in a very basic analysis, as far as just straight up pulling it from out of the post or pushing it in, essentially all it is just a fixed geometry or a prescribed displacement showing that it's going to move from right or from left to right. And when I run the analysis, I'm able to see the stresses again, that develop as I unclip that. So when I animate this here, let me change the view. You see what's happening, right? Let me slow this down for a bit. Essentially, we have a combination of not only the context changing as it's moving or getting unclipped from the post, right? We're seeing that deformation as well. And this is what you can currently do, without adjusting the time of the fixture. But this may develop some artificial stresses, or maybe you want to simulate it actually being pried open with like a screwdriver. You want to open it up first and then take it out of the clip. That's where you would want to do that on and off type of fixture. Where you see what I defined was for this specific fixture here, or excuse me, not this one. If we take a look at this, so I'm saying for like this face here, I want to control when this opens up essentially. So what I did was I varied that contact or that fixture as a function of time, and I'm saying that from at 0 seconds nothing's happening. At 0.18 seconds I want to move this face 1 times whatever value that I input here. So essentially I'm moving that face 1 millimeter at 0.18 seconds. And then at 0.35 seconds I want to ignore that fixture. So essentially what I'm doing is I'm prying it open, and then at the same time, in the same time domain, I'm going to say pull that panel away from the actual post. Right? So it's about playing around with some of the time domains. So essentially now that fixture is off at this point in time, and then at 0.18 seconds still off, or it's going to see, or it's pretty much going back to its original shape of 0 times whatever value I input here, and then at 1 second I want it to be fully open. Right? So it's maybe a little bit confusing in terms of lining up the actual time domains, but we're controlling when that fixture is going to play a role within our analysis. So when we view our results here, now for the open and pull, if I take a look at the stress, you'll see that there is kind of this snapping on and off. So let me change the view here. All right, so when I animate this, it's prying it open, and then we ignore the fixture, and that's where it kind of like snaps back to the post, and then we retract it, right? And that's what we're able to control to add maybe a little bit more realism in terms of how this is getting unclipped. Right? And why is this important? Because again, if we go to the original model, it may encounter or it may develop some artificial stresses that may not actually be there in real life. So if I were to do, the reaction force of, as far as what force is needed to actually pull it off or pull it out of the post, well, I can take a look at that, right, with the reaction force, and you see that for that direct pull portion that we did, it needs about a little over 20 pounds to actually take it out from or unclip it from the post. If I introduce that on-off for the actual fixture, if I do the same thing here, you'll note that we actually lowered the stresses due to this more realistic behavior as far as how we're going to unclip it from the post. So it went from a little bit of over 20 pounds to less than 20 pounds. So we lowered the amount of force that's required to actually unclip it from the post, right? And this is probably going to be a more realistic condition as far as making that assumption of maybe we're prying it open and then unclipping it, right? So those are the things that we can do within a nonlinear as far as being able to manipulate some of these conditions, the force, the fixtures, within the time domain, which we clearly can't do in a linear static study. Okay, so hopefully, that explains, kind of briefly the difference between linear and nonlinear, and hopefully, more importantly, when you should graduate from a linear static study to a nonlinear. Right? So the last thing that I want to do here is talk about SIMULIA Abaqus. So SOLIDWORKS simulation can of course do nonlinear problems, but SIMULIA Abaqus takes nonlinear to the next level. And what I mean by that is SIMULIA Abaqus allows us to do more robust, more complicated nonlinear problems like what you're seeing here through the animations, right? Kind of that clamp, getting clamped down into those cables. We wouldn't really be able to do that within a SOLIDWORKS simulation nonlinear, mainly because there's a lot of contexts that are changing, as a function of those different parts, where you're maybe hitting kind of a wall in terms of how much we can manipulate inside Simulation Premium. So this is where Abaqus can really help into these more complex type of problems. Right? It's a full multi-physics type of analysis. You see there that we can incorporate fluid with the actual component or with the actual tire there and see the behavior within that. It's a good tool for really large distortions, distorted models, any crash events, things that are crumpling within each other. These are things that are very highly nonlinear problems that we just can't really do within Simulation Premium, so then we can graduate to SIMULIA Abaqus. That is something that you can purchase. It is something that we offer within our SOLIDWORKS simulation services as well, in terms of if you do have a very complex problem, that is something that we can help you out as well. Right, and here's just a few examples. Right, SIMULIA Abaqus is a great tool for many different industries, just like Simulation Premium or simulation in general. Right, and you see, kind of more examples of the animations that we can do, or the types of problems that we can do through the animations. It's a great tool for drop tests, being able to see how things are kind of buckling within each other, breaking, collision. So the types of problems that we can do here are really complex nonlinear problems that we may be hitting a wall with Sim Premium, but that we can definitely do with SIMULIA Abaqus. All right. So and I briefly mentioned the services that we offer. A lot of the things that we do these webinar Wednesdays all the time, and some of them are simulation topics, but and that's really what we offer in terms of simulation in general, as far as resources for you, as far as more information that you can learn from, linear, static, or nonlinear. And we have our website that has all the webinars that we've ever done, for the year, that goes into different topics. We have our blogs as well that are posted. We have a YouTube channel with many different simulation videos there. But you also have technical support. So hopefully you're utilizing that. We have a dedicated engineer staff that talks about simulation, from your linear static to your nonlinear, or maybe any other product that you have within the family of simulation. And then of course we have training, right? There's a lot of things that I went over that hopefully made sense, but if you're definitely getting into this and you want to learn more or want to learn these functionalities, we can definitely do that through our training process, whether you do it online or in person. And if you are interested in SIMULIA Abaqus, or if you do have a problem that's very complex, or you're finding that you may not have the appropriate tool at the moment, we can help you out with that. We can do a mentoring session or a consulting session with you, where we can take your actual problem and either do it for you or teach you how to set up that problem with the appropriate tools. Right, so we have a lot of great things to offer within simulation. All right, so that's really all I had prepared for you. Again, feel free to ask any questions within the questions box. This is where I'll take some time to answer that. But I just want to thank you guys for joining me for today's webinar Wednesday. Again, we do this every Wednesday at 11 a.m. Next week we have the topic coming up of 3D scanning capabilities, 3D printing. Really pretty cool stuff that we can do with our 3D printers. And then the week after that, talking about designing electronics with SOLIDWORKS PCB. So if it's something that's an interest to you, definitely register just like how you did for this webinar. But if you have any other questions on the technical side or sales side, feel free to contact us. Feel free to ask me within the actual chat box here. But here's the contact information that we have. Right? If you have any questions in regards to that, let me know. Again, I want to thank you guys for joining me in today's webinar Wednesday. Hopefully you found it useful, and Have a good day.